Mr. Marshall, and this is going to start our unit on momentum. So momentum, maybe you have some kind of idea of what this is talking about. Newton always talked about momentum as kind of a quantity of motion. A fast-moving paper airplane has a velocity, but a large truck with the same velocity has more, but more of what? And that's described as momentum. It's a combination of both the velocity of an object and the mass. Because remember, mass, the more mass something has, the more inertia something has, or its ability to resist a change in motion. So a truck with a lot of mass is an object in motion that wants to stay in motion. A paper airplane has much smaller mass, so it has, you could say, less ability to stay in motion. Our equation for momentum is what, I could say simply, but what it is the mass of an object in kilograms and the velocity of an object in meters per second, and that gives you momentum. It's symbolized as a P because, well, M is clearly already used. Velocity has a direction, so momentum does too, which means you can add a negative momentum and a positive momentum, and those signs matter a lot. Momentum is directly proportional to mass. That means if momentum goes up, mass goes up. Maybe I should have put it the other way. If mass goes up, the momentum goes up. It's also directly proportional to velocity, meaning if one goes up, the other goes up. We're going to take a little bit to make sure you're clear that the units for momentum are kilogram meters per second. That's important because if you remember, a Newton is a kilogram meter per second per second. So the difference between force here and momentum here is really just essentially dividing by seconds, or another unit of time. And that brings us to the next equation, which is for impulse, but it's also looking at how impulse changes over time. If you want to change an object's velocity, you have to apply a force. So if your momentum is changing in kilogram meters per second, if it's changing over a unit of time, meaning your kilogram meters per second are changing per second, that's a unit of force, or a Newton. You can, of course, also write this to say that momentum is equal to a force being applied over a time. 5 Newton push against a chair is going to increase the velocity over, if you push for 1 second, the velocity will increase even more if you're pushing for 2 seconds, and so on. So here we've got impulse, which is a change in momentum. So basically, impulse and momentum are talking about the same thing, but you have an impulse when the momentum changes. We will be looking, maybe not in this abbreviated year, but we do look at sometimes an impulse can be a changing mass, but almost all of our problems, an impulse means you've changed your velocity. Changing your velocity is a lot simpler than changing mass, but we do have some problems where it snows on a boxcar and it gains mass or something like that. Okay, these are kind of the equation circles. Okay, triangles, sometimes we use circles. Momentum is mass times velocity, and we can also write that momentum is force times time. So the way that these work is, if you're solving for velocity, velocity equals momentum divided by mass. Velocity is momentum divided by mass. If you are solving for mass, you have momentum above velocity, or mass is momentum divided by velocity, like that. The position of the triangle is very important if you're solving for force, momentum over time. If you're solving for time, the momentum is on top, force is on the bottom. Like that. So that's these circles or triangles, sorry, sometimes I use circles, sometimes I use triangles, but those two are called mnemonics. They're just to help you put three variable equations together, and they're going to be great when we do electricity and Ohm's law. So the impulse momentum theorem is basically your airbag theorem. When your car goes from 60 miles an hour to 0 miles an hour, big change in velocity, there's going to be an impulse exerted on you. If that change in velocity happens in a very small amount of time, it's going to be a very big force. What an airbag does is it makes the amount of time that you come to a stop, it increases the amount of time. So if your time is somewhat big, your force goes down. And that's super important. And oh, here it is. Boom. If that change in momentum happens in short time, it's big force. Change in momentum happens in a big amount of time, it's a small force. Again, similar example to the airbag. Runaway green truck goes from 60 to 0 miles an hour, but here it hits a hay bale and it comes slowly to a rest. If you hit a tree, it's going to be a much huger force. So here we've got a problem that involves some numbers. So I didn't give these wrong numbers. But the idea here is we want to come up with how much momentum the baseball starts with, ends with. Change in momentum means impulse. So the initial momentum, mass times velocity, and we can put in a mass of 0.145 kilograms. We can put in a velocity of 35.7, and then we simply follow through on the math. Kilograms times 35.7 meters per second, and we have an initial momentum of, everybody watch me push buttons, 0.145 times 35.7, boom, 5.18 kilogram meters per second. That's a 5 too. Okay, so this is our starting momentum. If it comes to a stop, the mass doesn't change, the velocity does. You've got a mass of 0.145, a velocity of 0. Watch me punch the nut. No, all right, you don't have to punch the numbers in because the final momentum is 0. So what happened to your momentum? You started with 5.18, you ended with 0. Your change in momentum or impulse is final minus initial, or negative 5.18 kilogram meters per second. So this is the most basic form of a momentum problem, where I give you a mass and a velocity and ask you to come up with momentum, straight 3-variable multiplication, not too much of a trick about it. How much force was required was just taking it one step further. So we know that the momentum was negative 5.18 kilogram meters per second. The time is 0.1. We know that force times time equals momentum. So, and again, if you flip back a couple slides, I use that triangle to kind of rework that to say that time equals momentum divided by, oh wait, I have time. That's going to be an eraser move. And force equals momentum divided by time. 5.18 divided by 0.1 should be 51.8 newtons of force, negative, because it was acting to stop the baseball. So that's kind of the basic form of an impulse problem. This is the kind of advanced-ish application of what we're talking about. This is where you've got an object with momentum going in one direction, an object with less momentum going in the other direction. When they collide, the one with more momentum wins. So if my fist has 10 kilogram meters per second, 2x2 puzzle cube has, I'll just say 8 kilogram meters per second. Boom, the fist is going to win by how much? By 2 kilogram meters per second. That's the momentum, the net momentum of that collision. And then we can figure out the velocity if we know mass. We can figure out mass if we know velocity, etc. So here's our practice problem. During a football game, we have a 90 kilogram running back moving east. So we'll go ahead and do some compass rose stuff. East is going to be positive, west is going to be negative. That's important because one of these sides is going to win and one's going to lose. He's tackled by a 110 kilogram defensive lineman running west. So that's going to be negative. Both players move east after the collision. So I've kind of color-coded this because it can be hard to keep track of linemen and stuff like that if it's not your sport. So it starts out momentum of the defensive lineman. That's blue, I think. So it's 110. So we want the momentum. Boom. I have a mass of 110 kilograms. That's here. And I have west at 5. So his velocity is -5 meters per second. So 110 times -5 should give you -550 kilogram meters per second of momentum before the collision. So what's the momentum of the two players after the collision? So this type of thing you do have to read a little bit because you have to say, okay, after the collision in green, it is going east at 1.5. So the velocity is 1.5 meters per second in the positive direction. I give you this nice hint about combined masses. So the combined masses are going to be 90 and 110, which by my math is 200 kilograms. Masses don't have a direction, it's just mass. So the momentum of the two of them is going to be their combined velocity of 1.5 times their combined masses of 200, which should be something like positive 300 kilogram meters per second. Okay, so defensive lineman has negative momentum. He collides with the other player, running back. Boom, they end up going in the positive direction. So it kind of has to be that the running back had more momentum if when they collide it's the running back that wins. So the question about the running back, well, I know his mass was 90 kilograms, but I don't know his velocity. But what this problem is saying is that if you have the momentum of the running back, RB, plus the momentum of the lineman, so those two are colliding, and afterwards we have a momentum, I'll just call it total. That's what happens in a collision. The momentums are combined. In this case, we have a total momentum of 300. I have a lineman momentum of -550. So how could you end up doing this math where the momentum of a running back collides with the momentum of a lineman and the result is a positive momentum for the two of them. And if this was simple math, you'd say, well, that means that the running back has to have more than 550 kilogram meters per second momentum. How much more? 300 more. So, you know, question mark. The answer would be to add 550 to both sides, and the momentum of the running back works out to be about 850 kilogram meters per second. And this is kind of the complicated version of these momentum problems, in case you haven't realized. And our last step is to say, well, if I know the momentum is 850 kilogram meters per second, and I know the mass is 90, well, from here I can just say momentum is mass times velocity, and I can figure out, well, velocity would be momentum divided by mass, and that's 850 divided by 90. So this will work out to be 9.4 meters per second, and it's positive. Okay, so I've zipped through a lot of these problems. I get that. Momentum is about collisions. The quantity of motion that an object has is consisting of both the mass of the object and its velocity. In outer space, collisions are tough because you'll typically have tiny pieces of matter, tiny pieces of steel left over from different projectiles we've sent up there, but they're going so fast that they have a lot of momentum and a lot of energy. So I'm going to go through a couple of the problems that I'll put in forms for when this is done. I'm going to use football again because it's kind of a good analogy. Johnny D's middle linebacker for South's varsity football team in a game against North. He hit North's running back. So North's running back is 82 kilograms, changing the same running back's eastward velocity of 5.6. So we're going to keep east as being positive. And after the hit, this same running back goes west, which is negative, at 2.5. So the first question, initial momentum, is just going to be his mass times his velocity. That's easy enough. Final momentum is still mass times velocity. And remember, it's just this running back. So he's still 82 kilograms. He's still 82 kilograms. He starts out going 5.6 meters per second in the positive direction. He ends going 2.5 meters per second in the negative direction. That's a change in momentum. And the change in momentum is simply at taking your momentum final minus momentum initial to get that change in momentum. And then determine the impulse. This is just a play on words. Impulse is change in momentum. So you're not trying to figure out time or doing any other type of division stuff. Impulse is change in momentum. Those two numbers are the same. Little tip. So the next slide, it may look like a simple problem, but there's a little trick to it. So for this one, there's a friction force. So this should make you think impulse, because if there's friction on, well, on a 70 kilogram skier for 20 seconds, you should kind of get that idea in your head. Oh, that means he's going to slow down. So that means his momentum is going to change. Change in momentum is mass times that change in velocity. And we can also write this as our change in momentum is force divided by, force times time. Now, the trick to this problem is that we don't care what the initial or final velocity is. All we care about is that change in velocity. And that works out to force times time equals mass times a change in velocity. If I divide both sides by m, the m divides off to become 1, and it's just force times time will tell you how much the velocity changes. Don't care about the initial or the final.